Programming is a method for finding a minimum or maximum value of some quantity given a set of constraints. So the set of constraints, that's where we're going to build the inequalities or the equations. The constraints in a linear programming situation form a system of inequalities. That's where we graph the lines, shade the region that makes all the inequalities true. We'll still think about dashed and solid lines here. So this is kind of an example of those constraints and the systems of inequalities. The graph of the system is called the feasible region. So that's worth kind of taking note. There is some language associated with this here. Feasible region is the region that we shade. So inside that shading, those are all the points that meet all the constraints of the given linear programming problem. The quantity you're trying to maximize or minimize is modeled with what's called an objective function. That objective function is something completely unrelated. I shouldn't say unrelated, but not necessarily something we see when graphing the constraints. Okay, so know that your objective function is a completely different equation than all of your constraints. So let's make a note of that. Okay, so different equation than constraints. And using the objective function, that's what we're usually trying to maximize or minimize. So let's also make a note that this is what we try to max or minimize. Often the quantity is cost or profit, so a lot of these types of problems are related to kind of business models. Again, in here we're not going to do anything super in-depth, so they'll still seem a little silly, but a lot of it relating to cost or profit. Graphs of the objective function are various values of C are parallel lines, and that's what this is showing down here. So this line right here, this is a potential. These are potential objective functions. Okay, and so you can see, like in this case, that 17, that value being greater than the 7, we would say that the line that passes through this point gives us a maximum value. And again, that'll be kind of our focus as we work through the problems here. But that's what this is showing, just how that objective function is different than the feasible region, and that's what we use to maximize it. The vertices. So again, there's more language associated here. Vertices are like the corners of your feasible region. And let's maybe make a note of that as well. So vertices, corners. And it's these vertices of the feasible region that represent either the least and the greatest values. So it's one of those vertices that's going to allow us to maximize or minimize the objective function. So when we're going through this whole process, it's a set of steps where we'll work to build our constraints. We'll graph the constraints, find our feasible region, make note of what the vertices are, and then use the coordinates of the vertices to see which of those gives us the largest value for our objective function. So you can solve problem using linear programming by testing in the objective function all of the vertices. So exactly what I just mentioned. Okay. So just to get us going, we'll skip, there's no associated word problem here, but this kind of paints a picture as to what we'll do after getting the constraints and the objective function. But again, the hardest part is going to be taking the word problem and how do we get these constraints and or the objective function. So right here, this is our objective function. That's always something I'd kind of take note of right from the start. And what we're going to go ahead and do is just graph these lines right off the start. So x being greater than or equal to 0, that means that when we graph this, all the x values need to be positive. So we're going to put a line on the y-axis. That's a solid line, and that's the x being greater than or equal to 0. Same thing for y being greater than or equal to 0. That means we need all the y values to be positive, and thus we're working in quadrant 1. I think this pen is done. Then these other two lines, again, they're not in a great form that will allow us to graph right now, we can find intercepts, or even better, getting y by itself. And I'm going to do that. So the top equation is x plus 2y is less than or equal to 5. So I'm going to subtract x. So 2y is less than or equal to 5 minus x. And then divide by 2. And get that y is less than or equal to 5 halves minus 1 half x. Graphing that is not the most accurate, since we're going to have to put it in between some coordinates, but that's okay. So let's go ahead and graph this just right now. Y-intercept of 5 halves, which is 2.5. And then my slope of negative 1 half, telling me to go down 1 and right 2. Down 1, right 2. And we could also go down a half and over 1. Would also work. Just to get that point there as well. This is a solid line. And y needs to be less than or equal to this line. So right now, our feasible region is this shaded section, is this like triangular section created by the axes and the line we just graphed. Our other line, x minus y being less than or equal to 2. Again, we need to subtract x. So negative y is less than or equal to negative x plus 2. Then divide by negative 1, where we get y, and the sign flips from less than or equal to now greater than or equal to, and that'd be x minus 2. So start at negative 2, a slope of 1 tells me to go up 1, right 1. And this is also a solid line. And so our feasible region is either this quadrilateral section right here or this triangular section, because we knew we needed to be below the first line we graphed, and now we need to be above this line that we just came up with. So above the line with a y-intercept of negative 2. That makes this feasible region right in here. So after graphing our feasible region, the next thing we'll want to do is take note of the vertices. So the vertices, we have one right here on the y-axis. That coordinates, or those coordinates, are 0, 2.5. We have 0, 0. We have this point on the x-axis, which is 2, 0. And then these lines intersect, it appears at 3, 1. So these are all of our vertices. And if you notice, those are also the choices. This was a multiple choice question, where our task is to figure out which one of these points, or in this case vertices, is going to maximize the objective function. Now, if you notice, the objective function has 3 variables. But using the vertices, we have an x and a y, allowing us to solve for that third variable, in this case p. So what we'll do is we'll take our objective function, so p equals 2x plus y, and I'm going to sub the x and the y into these equations and see what value of p we end up getting. We are looking for the one that's going to give us the largest value of p. So p equals 2 times 2 plus 0, so in this case p equals 4. Then we've got 0, 0, which if we're trying to maximize, I think it's pretty clear that that's not going to be a value that maximizes our objective function, because we just get 0. 3, 1, I'm already thinking is going to be bigger than the ones we've already found, because I have 2 times 3, and then plus 1, so that's 6 plus 1, which is 7. And the 0, 2.5, I already know that's not going to maximize it, because we have 2 times 0, and then there's plus 2.5. So giving us just that p is 2.5. So in this case, the value that gives us the largest value for our objective function is 3, 1. So it's this point right here that maximizes the objective function. And that's always going to be our task. Okay, which of the values either maximizes, or there will be some cases where we minimize the value given the constraints. So the only thing we did not do here is we did not have a sort of situation explaining where these constraints came from and or where the objective function came from. And that's what we're going to do here in just a moment. So go ahead and flip this page over once you've all caught up here. What we're going to do is I'm going to go through the first one and then have you all work through the second one in class. We'll still check them all together. You know what? Why don't you just do this right on your own? Let's just do that right now. And then we'll go through two together. I had my stuff mixed up. So it says graph the system of constraints, name all the vertices, then find the value of x, y that maximize or minimize. Let's find both. Which one maximizes, which one minimizes the objective function. So basically what we just did, go and do that on your own. We'll check our work here. Right now, I just need you to try this. Because once I'm done, I show the work. We'll be pretty quick to transition to that last problem. Right? So do your best. I'll give you all like 5-ish minutes. It'll take some time. I'll take attendance. And then we'll move on to the actual word problem here in a second. Oops. You caught that? It doesn't say the song's explicit, so I don't know all the words of that song, clearly. Oh well. Oh, sorry, I'll pause. So nothing too bad here. Again, getting your lines into a form where they're easily graphable is a good idea. So solving them for y, in both cases, that's pretty quick, just subtracting x and then subtracting 2x. And then, yeah, we find that those two lines intersect at 2, 6. So that's one of our vertices. All the other vertices are on one of the axes, so either 0, 0, 0, 8, or 5, 0. And that's, again, based on the shading. We're below both lines. And so below both lines makes this kind of quadrilateral section. I want to call it a trapezoid, but it's technically not a trapezoid. But anyways, after finding those vertices, plugging in the corresponding x and y into the objective function, again, we're just thinking about which values give us that largest value of n. That's always going to be the value we try to maximize. Okay, either the n or whatever the objective function is equal to. The one that actually maximizes it, when I first look at this, I'm like, the 2, 6 will maximize it for sure. But because the x value is getting multiplied by 100, it actually ends up being that 5, 0. Okay, because we get 500 there as opposed to 440 for the 6, 2, or the 2, 6, excuse me. 0, 0 gives us the minimum. We just get 0 there. So hopefully that's fairly straightforward. Okay. Any questions here before we add in that next element of actually having to come up with our own constraints? I have actually one more thing I want to add. Let's pretend that I could not find that point of intersection. Like, let's say it intersected like in between some numbers. Do we have a method for how we could figure out where those intersect? I can think of 2 off the top of my head. Casper, you're shaking your head up and down. What's one? Elimination. What's the other one? Someone say it louder for me, please. Filippo, what'd you say? Substitution. Okay, so if we can't find the points of intersection, we could take our equations. Okay, yes, they're inequalities, but we can turn them into equations, and we can substitute. So I could go y equals negative x plus 8, y equals negative 2x plus 10. We could substitute in for y and solve for the point of intersection. That might be one thing we have to do when you get to your homework section. Okay, so that's why all of this is tied together with every single thing we've done this unit thus far. We're writing equations, graphing systems of inequalities, and potentially even solving a system to figure out where they intersect. Okay, so again, if you can't find the point of intersection, use an algebraic way to find that. Okay, so now to the application. And again, there's a lot, right? And what's hard about the word problems is our reading skills factor into this. And I've shared with you all before, my reading skills are not the best. Okay, that always is one thing that kind of held me back as a student and I really had to work at. So one way to help me manage that is as I read this, I'm going to write down all the information I know. So my task is first going to be to pull out the information I need and figure out how can I build that in constraints. So let's read it and then kind of get us an idea of where we're going to start. So baking a tray of corn muffins takes 4 cups of milk and 3 cups of wheat flour. Baking a tray of bran muffins takes 2 cups of milk and 3 cups of wheat flour. A baker has 16 cups of milk and 15 cups of wheat flour. He makes $3 profit per tray of corn and $2 profit per tray of bran muffins. How many trays of each type of muffin should the baker make to maximize his profit? So already I can see where the objective function is coming in, right? It's what are we trying to maximize, and we're trying to maximize the profit. So let's make our objective function just right off the, actually, let's define our variables first. So what are we trying to find? We're trying to find the number of trays of each type of muffin the baker should make. The defining of our variables always comes back to what are we trying to answer? And it's how many trays of each type. So we'll let X be the number of trays of corn muffins. And then Y be the number of trays of bran muffins. Okay, so even with the word problems, defining your variables is a great place to start. So then let's list what do we know about each. So to bake a tray of corn muffins, we have 4 cups of milk, 3 cups of wheat flour, to then bake bran muffins, we need 2 cups of milk, and 3 cups of wheat, so 3 cups for each. And then the only other thing, and one thing I might do is cross off once I've kind of made a note that I have all this information written down somewhere. The last cup or the last piece of information is just the total amount of ingredients this baker has to work with. So in total, we have 16 cups of milk and 15 of wheat. And this is where this can be a little bit tricky and why I think the defining of variables is so important. Because at first, when I read this problem, I'm like, hey, one of my equations should represent how I make the corn muffins. The other equation should represent how I make the bran muffins. But as I lay this out, I'm like, that doesn't make sense because if my variable is related to the trays, well, each tray is going to have different types of different type of each ingredient, and our ingredients are limited. So now I'm thinking instead I'm going to have an equation to represent the usage of milk and then the usage of the wheat flour. Okay, so another two constraints that hopefully should be obvious is, the negative trays make any sense here? Not at all, right? So right off the bat, we can say x needs to be greater than or equal to 0 and y needs to be greater than or equal to 0. Okay, so we can make 0 of one type of each muffin, but we can't make less than that. Then, if making my equation for, let's start with the milk and the usage of the milk, I'm like, okay, there's 4 cups of milk for one tray of corn. So that's 4x plus 2 cups of milk for one tray of bran, so 2y, and that has to stay less than or equal to 16. So that's again representing our usage of the milk. We'll do the same thing with the wheat, where our usage has 3 cups of wheat per one tray of corn muffins, so 3x. And then plus, same thing for the bran, 3y. And that needs to stay less than or equal to 15. And so now all of these pieces of information have been dealt with. The only thing left over is that profit, okay? So how the baker is making money. That's one last thing we need to add in. It's not a constraint. I should have added a place for us to write our objective function. So let's just make a note that the objective function where we're trying to maximize profit, so we'll say P is equal to how much money per tray he sells. So $3 profit per corn muffin, so 3x, plus $2 profit of bran, so 2y, 3x plus 2y. This is a perfectly okay to write your objective function. On one of your homework problems, you're going to see it written like this, P of xy, just to keep it in that function notation. This is the same thing as P just equaling 3x plus 2y. This is just saying the profit is a function of the variables x and y. So this is your function notation. This is like your classic way of writing an equation. So just know that these are the same. All right, so that's the only new thing we added into the linear programming problem. Now we can graph these, track down our vertices, and figure out which of those vertices maximizes the feasible or maximizes the objective function. So got to be greater than or equal to 0. Our graph is already set up for that. Then I'm going to get these equations in a form where I can graph them a little bit easier. I'll do that over here. I don't have a ton of room for that. So 2y is less than or equal to negative 4x plus 16, which means that y is less than or equal to negative 2x plus 8. And then we also have 3y is less than or equal to negative 3x plus 15. So y is less than or equal to negative x plus 5. Okay, so negative 2x plus 8, I'm going to go up to 8. I'm going to go down to right 1. And we need to be less than or equal to that, so we're below that line. And then negative x plus 5. So down 1, right 1. Down 1, down 1, right 1. And now we just need to make a note of all of our vertices. And you can write it on your graph, or you can just write them on the side here. And again, our shaded region, we're below both lines, so it's this quadrilateral section. Again, that's, I guess, nope, not a trapezoid still. There's no parallel sides. And so our objective, or our vertices are 0, 0, 5, or 0, 5, 4, 0, and this is at 3, 2. So now we just need to check and see which ones maximize the profit. Some of them we can skip, right? Like the 0, 0, we don't need to plug that in. We know that's going to give us a profit of 0. Okay, so we can skip that one. Even though at first glance it feels like the 3 and 2 should maximize it, don't assume that. Always worth a quick check. So P of 0, 5 means that we have 3 times 0 plus 2 times 5. So that'd give us a profit of 10. Then P of 4, 0 would give us 3 times 4 plus 2 times 0, which is 12. So already the 4, 0, so selling all the corn muffins gives more profit, which makes sense because they're worth more. And the 3, 2 gives us 3 times 3 plus 2 times 2. That's 9 plus 4, which is 13. Okay, so based on the limited ingredients the baker has and how much he sells each tray for, the baker should make 3 trays of corn and 2 trays of bran. All right, and that's it.